Hi, this is E637. I'm Charles Bouman, and today we're going to pick up on the material we left off on last, which was the subtractive color image systems and the Limburgian surfaces. So, if you just recall from the last time, we were talking about the color cube, and basically K is the black, and W here represents white, which is usually assumed to be the paper color. So this is kind of a qualitative color system as opposed to precisely quantitative as I'm presenting it here. And then you put colorants or inks or dyes on the paper and when you put the dyes on the paper, if they're not fluorescent, then they can only absorb light. They can't produce light. So they subtract color out. So if you put all the different colors on the page, then what happens is you get black, at least in theory. In practice, it may not quite work out that way because for various physical reasons, but you'll get at least an approximate black. And then, but if you just take away the blue, you'll get yellow. So if you take the blue out of white, you get yellow. If you take the red out of white, you get cyan. And if you take the green out of white, you get magenta. So you have this cube with 8 corners, 8 vertices. And white is what you get when you put nothing down on the paper. So this is sort of the reverse of what you have in a display. In a display, you add the colors, right? You put red, green, and blue together. When you see all those colors together, you see white. But in printed material, you're subtracting color away because when you put dyes or inks on the page, they absorb light, and as you remove more light, eventually you get the black. So it's now, of course, you can use the same color coordinates to describe either process, but one is more natural than the other. So often printers will be described in CMY coordinates, or cyan, magenta, yellow, whereas displays are described in RGB. So now, if you have a Limburgian surface, I talked about this before with the light reflecting off the surface of the moon. The light goes in, it scatters around, and it comes out in a, well, what I might call random direction. Okay, it's not really. What does that mean? It's not very specific. Well, you can show that if a lot of scatter events occur at the surface and the light is not absorbed, it just bounces around. When it comes out, it's going to turn out that the intensity of the light is going to be inversely proportional to the cosine. Okay, it's going to be proportional to a cosine, and then when you look at it, what happens is the angle subtended at high angles, that the amount of surface you see for a specific angle subtended increases as 1 over 2 cosine. So those two factors of cosine cancel out. And the bottom line is that when you look at a Limburgian surface at an angle at a distance, the surface brightness is invariant to the angle of the surface, if it's a perfect Limburgian surface. So that's kind of how it works. But then what happens is that you put inks or dye on the page, and as light goes through, the light is absorbed. Now, if you recall, when we talked about CT or computed tomography, we talked about what's called Beer's law, where the light is absorbed exponentially as it passes through a material. So what happens here is the absorption, it becomes a function of wavelength or frequency, wavelength. So at some wavelengths the absorption is more rapid, and at other wavelengths it's less rapid. And but the important thing is that the absorption of different materials, assuming that the light goes through, bounces off the surface, and comes back, okay, which is an important assumption, the effect is multiplicative. In any case, it's a nonlinear effect. So the reflected light is the illuminant. I here is the illuminant as a function of wavelength times the two materials, the product of the two materials absorption spectrum. So you can think of this as like a filter in linear time invariant systems, that these are filters as a function of wavelength. So you multiply these all together. So this is nonlinear because it's not additive, it's multiplicative. Okay, now to get some intuition as to how that all works, so let's say that if you start off with white light, if you put cyan ink down, then what happens is, and this is just conceptual, right? I mean, it's not quantitative. But the spectrum would be approximately flat, because if the illuminant's white. If it's what's called an equal energy white, it might be closer to flat. In practice, real illuminants never have a perfectly flat spectrum, but let's say it's approximately flat. Then the cyan will absorb the long wavelengths of the light and allow through the short and the medium wavelengths, right? And then the magenta will absorb the medium wavelengths, say. It's not exactly like this, okay? As you know, the human visual system responses, the color matching functions are complex, but this is just sort of almost a cartoonized version of it, just to give you the logical sense of what's happening, okay? And then if you put both the cyan and magenta down together, what happens is that these multiply. So they're almost like logical gates. This is stopping the light here, and this is stopping the light here. So if you take the product of the two, you'll stop both, and you get this. So the combination of cyan and magenta is going to produce something with just short wavelengths. So that's going to appear blue. So if you put cyan and magenta colorant together, you get blue, right? Which can also be then explained by the color cube, right? So if you first go in the direction of cyan, and then magenta's down, so that would be here, so it would take you to blue. Or the other way you can go is first go to magenta, and then go to cyan there, which is blue. Okay. Okay. All right. Good. Okay. Now, the next topic I think is really interesting to me, and it's the part I think that it's the mathematical underpinnings that, at least in my mind, sort of pull this all together in a sensible framework. The chromaticity coordinates. So far we've learned a lot of different things, but they seem a little disconnected, okay, at least in my opinion. So for instance, we have this idea that you can have RGB color matching functions, and then there's primaries associated with those, and then we get tristimulus values, but the problem is the tristimulus values can be negative, right? Then we talked about XYZ. XYZ, the tristimulus values can't be negative in XYZ, but the problem is that the color match, so that's good, the color matches are positive, but the problem is that the primaries associated with XYZ don't exist. Or at least I claim they don't exist. I didn't really prove it. Every time we went to look for them, they didn't seem to be there, okay? In this section, I'm going to be able to prove, essentially mathematically, it's a combination of math and some empirical measurements, that those primaries don't exist, that there's no coordinate systems, there's no colors, there's no physical stimulus we can produce which will produce the sensation of a pure tristimulus value of X with no Y or Z. So what does that mean? It means that you can't match to that. You will never do a color match to that value. There's no physical stimulus that you can produce for a person with normal vision that will color match to that value. So that's what makes it an imaginary color. It's a mathematical concept, but it doesn't physically occur in practice. And the color chromaticity coordinates will give us the mathematical underpinnings to understand why that's the case. Okay? So now, chromaticity coordinates are a very simple idea, really. You take the XYZ values, and remember, we assumed that the XYZ values were computed by assuming that the color matching functions associated with them integrated to 1. Okay? So so you take the XYZ values, and for each XYZ value, you normalize the values by dividing by their sum. Okay, so so you take x and you divide it by x plus y plus z. Now the x, y, and z are always positive, right? So we know they're always positive because their color matching functions are strictly positive. So if I divide x by the sum of x, y, z, I'll always get a positive value. And the denominator would be positive, the numerator is positive, this all is fine, okay? Assuming that the object is not a perfect black, then the divisor is greater than 0, and this is well defined, okay? Now I'm going to get three values, and I reserve the value, the notations lowercase x, y, and z to represent the three values, okay? And the lowercase x, y, z is are known as the chromaticity coordinates. So, well, now to think about this a little bit, it's a little, okay, at the risk of telling you something that's going to confuse you. Okay, if there were only two coordinates, x and y, okay, I'm going to draw a picture in that case because it's simpler to draw, okay? So if I drew, this is x and this is y, right? And then x plus y equals a constant is like this, right? Right, that's the line x plus y. If I take any other point here, okay, so then the chromaticity coordinates is what I get if I project that line to the origin. This is 0, 0, right? And I look at the intersection here. So this is some value x0, y0, right? And that's the chromaticity coordinates x0, y0. So these are script lowercase, and that's non-script uppercase. Okay. So this is called a projection. Projections have the property that, well, they have a few properties. One is that, they have the property that if I move, so you can imagine if I move this thing along a line, okay, in this axis, it's going to move along a line in this axis. This is a nonlinear transform, but it has many of the properties of a linear transform. A straight line in the real world is equal to a projection in the projected domain. So that's exactly the same thing that happens when you have, if you have perspective projection, right? In perspective projection, I mean, like, I'm like the worst artist in the universe, but let me see. How did this work? So if you have railroad tracks or something, it looks like this.
You're referring to the vanishing point?
Yeah, this is the vanishing point.
Mm-hmm.
Yeah, right. So does that look like railroad tracks? Okay. That's our approximation to railroad tracks. So, oops, these are railroad tracks. And I guess these would have to get closer, okay? But the point is here, if you have railroad tracks, right, and then I guess, oh gosh, does that look right? Actually, I could have done this actually and just used the projector to do this, right? We should be. Oh, the problem is that they've set this thing up to be almost parallel projection, right? So they use the camera. I'd have to get the camera really close over here. I don't know if it would remain in focus. Okay. We should be able to do an experiment on this. Okay. Okay. Anyway, the lines should be parallel. Okay, but they should disappear off into infinity, right? So they get closer together. So anyway, parallel perspective projections have the property that straight lines in the real world remain straight in the picture. Okay, so anybody who's ever taken an art lesson should know that. Okay. Okay, so, and looking at it this way, it seems reasonable, right? So that's a very powerful concept that we will use. It's very clever, okay? So one thing that happens is that, first of all, first of all, we know that little x plus little y plus little z, oops, oh gosh, okay, let me do that again. Little x plus little y plus little z have to equal what?
1.
1, because we constructed it that way. We normalized them so that they sum to 1, right? So we know that's true. So since we know that they're all true, that means that if you give me x and y, I can calculate z, right? Because z must just equal 1 minus x minus y, right? So that means that usually what happens is you don't bother giving z. You just give it x and y, because that's good enough, okay, mathematically. Okay, so that's one thing. So you don't need to know them. And then the other thing is that if I take any alpha greater than 0, right, then and if I take alpha times x plus alpha times y plus alpha times z, right, and if I map that to chromaticity coordinates, right, I get little x, little y, little z. Oops, oh gosh, little z, okay. That will give me the same thing as if I took the original x, y, and z. I'll get the same chromaticity coordinates. So now, you've got to be a little careful. The chromaticity coordinates don't tell you the color, okay? Because the color is more than just its chromaticity. You also need to know the lightness. So it's not, so basically, by this definition, white and black have the same color. Okay, well, I mean, they have the same chromaticity. Well, assuming it's not a perfect black, because then the chromaticity is ill-defined. But or white and gray, a neutral gray and white have the same chromaticity, but they don't have the same color. Okay, so you have to be a little careful. But this tells you the an important characteristic of the color. Okay, so now, but most important, or one, well. Most important, extremely important, is that straight lines in the XYZ space correspond to straight lines in the chromaticity space. So this is a powerful idea. Now, I have a proof here of this being the case, okay? But I will skip it because I'll let you just verify it that it's true. It's pretty intuitive because I drew this picture right here, right? Now, the other thing that's the case is that if I take this diagram, this is x and this is y, and this is just a two-dimensional case, but the same concept's true in 3 dimensions, right? If I take, this is color 1, right? And so it has some, oops, oh gosh, I should have a ruler. This is color 2. Okay? And now if I take a combination of these colors, so if I take, say, some percentage lambda of this is C1 and this is C2, and this thing here is, this is C3, and C3 is equal to lambda times C1 plus 1 minus lambda times C2, right? So, right? That's a combination. And if I look at its chromaticity, okay, now what will happen is that this thing here I'll call, so this is going to be little x3, little y3, okay, will equal alpha times little x1, little y1, plus beta times little x2, little y2, right? And here, this is little x2, little y2, and this is little x1, little y1, and this is little x3, little y3, right? And alpha here, well, first of all, what will happen is that alpha plus beta equals 1, okay? So this falls on the line between here and here, so it's formed by a convex combination of them, okay? The other thing is this, that alpha will be between, alpha will be between 0 and 1, and beta will also be between 0 and 1. Assuming here that lambda is between 0 and 1. Okay? So it's not going to happen that, so the point here is that it's not going to happen that if this color falls between these two, that the chromaticity will fall outside the interval. If this falls inside this interval, then this has to also fall inside this interval. It's sort of simple geometry, right? But that's all proved in this calculation, okay? So I'll let you go through the calculation. So this is, I don't know, I can't remember whether this is left or right brain. But if this is the left brain, maybe this is the right brain, or vice versa, or something like that, okay? So for those in the room that are left-brained, you can think of it your way, and if you're right-brained, you can think of it your way, okay? I aim to please. Okay. Now keep those thoughts clearly in your head. And now what we're going to do is we're going to say, okay, now let's remember what XYZ is. XYZ is the inner product of the color matching function with the spectrum. So if I have just a single spectral component at wavelength lambda 0, then the color matching then the XYZ values I get are just the actual color matching functions evaluated at that value of lambda 0, right? So I can actually, then this is the color. So I can actually evaluate the color matching functions at each wavelength, and the relative proportion of X, Y, and Z is the color, okay? Now, so I can then ask, well, okay, so this would be the color I would see if I had a pure spectral source of light. Now, I can take that pure spectral source of light and I can ask myself, well, what is its chromaticity? To do that, I just plug into this equation. Because now I just normalize by the sum. And then this gives me the chromaticity of that pure spectral wavelength at wavelength lambda. And now I can plot this value as a function of lambda. If I plot the value as a function of lambda, I get a curve, okay? And before I show you the official curve, I'll show you the unofficial one that I'm going to draw here. Okay, so first of all, this is X. X cannot exceed 1, right? X cannot go below 0 and cannot exceed 1. Why? Well, because remember, each X was computed by taking the X here is computed by taking X and dividing by X plus Y plus Z, right? Now these are all 3 positive, so this X divided by this, and X is positive, so this must be greater than 0. And it can't be more than 1, because how could it exceed 1? Y here is can't be less than 0. So that means that the numerator must be less than or equal to the denominator, right? So it's always going to find, it has to fall in the interval 0 to 1, right? And the same thing is true of Y. So this is this is also 0 to 1, right? So now, by the same argument, you can argue that you can't exceed a line connecting these 2 points, because the sum of X and Y together, if I sum X and Y, it's got to also be less than 1, right? And that's what this line is, right? So we only have to worry about the chromaticities in this triangle. All the chromaticities must fall inside of this triangle. mathematically, it doesn't make any sense for them to fall outside because the quantities x, y, and z are all positive. Now, if I plot then the chromaticities associated with each value of lambda, so I'll have the chromaticity as a function of lambda, all right? So it's a two-dimensional coordinate. And then what I'll do is I'll get a curve. Now, let's say I start at so I start at lambda equals 400 nanometers, okay? So that's short wavelengths, that's blue. Okay, is it blue? No, it's not blue, not really, but I'm going to call it blue because, well, it's not green and it's not red, okay? But no one would really, I don't think people, if you were a color aficionado, you would not call this color blue, okay? But it's more blue than it is red or green, okay? So we'll call it blue, okay? So, and if you go any further, it's going to be ultraviolet, right? Now, so blue, okay, so let's see. X really represents red. It's sort of a supersaturated red. Y represents green. Not really, but just roughly. And Z kind of represents blue. So over here, you're going to be mostly Z. Now, if you're mostly Z, well, if mostly it's Z, then what will happen is X and Y will be small compared to Z, and the values of X and Y will both be close to 0. So over here, you'll be down here. So that's 400 nanometers. You're closer to the origin, all right? Now, at lambda equals 800 nanometers, that's like red. Or if you go beyond that, it's infrared. So this is going to be over red. In red, it's X equals 1, okay? So we're going to be over here, it's going to turn out. In between, when we're halfway in between, when we're, say, lambda equals, I'm just making something up here, say 600, because that's halfway between, that's mostly going to be Y. So over here, what will happen is that little y will be the largest, because this is little y. So over here will be here, okay? And in the middle, it's going to like we're going to take a walk. This is 800, and this is 600. So we're going to take a walk, and it's going to kind of go like this. So that's what the spectrum is going to look like in this chromaticity space. So this is the rainbow, okay? Now, what's going to happen now? Has anybody ever seen a rainbow with purple in it? No. If you have, you better go get your eyes checked or something, okay? Okay? No. Purple is not a member of the rainbow, okay? It's excluded, okay? So how do you get purple? Well, if you add red and blue together, you get purple. These are what are called extraspectral colors because they're saturated colors which are not part of the spectrum. Now, if I take any two colors and I mix them together, because of this projection property, it's going to fall in the line between them. Mm-hmm. So if I take a 400 nanometer and an 800 nanometer laser and I mix the colors from them, I'm going to get a line connecting them, okay? Okay, now, so now, let's say now I take any other point. Let's say I want to produce, this is such a nice diagram. I hate to mess it all up, but I'm going to have to. Okay, so let's say I want to produce that point right there, okay? I want to produce a color that has that chromaticity. Now, my first question is, if I give you the chromaticity of a color, is the color unique? No, because there's lots of colors that have the same chromaticity, right? As a matter of fact, if I give you the X, Y, Z values of a color, is the spectrum of that color unique?
Yes.
In general, no, because you can have two different you can have two different spectra that have the same XYZ tristimulus values, but the spectra are different. Why? Because tristimulus values are a 3-dimensional space, and color lives in at least a 31-dimensional space. So the one space is much higher dimension than the other. There's a lot of spectra that correspond to the same color. If two light sources have different spectra but have the same color in the sense of having the same tristimulus values, what do we call those two colors? Metamers. That's what a metamer is. You say something's a metamer if it has the same color, okay, but the spectra are different. That's going to come up in applications. We won't go into it a lot here. That will come up in applications because you can have two different materials that look to be the same color under one illuminant, and then they're under a different illuminant, they look different. That's because the underlying physics of what's producing the color is different. So they appear the same. It's almost like an optical illusion, you might say. They appear the same, but then you take it under a different illuminant, and they no longer appear the same. Okay. So there's two different levels of at least two different levels of sort of non-uniqueness here. Okay. One is the non-uniqueness of how you produce one color here from different spectra I'm going to get to, and the other one is this issue of metamers. Okay. Okay. But coming back to the original question, I want to reproduce that color. I know there's many colors that correspond to that chromaticity, but I want to reproduce a color with that chromaticity. Okay. How do I go about doing it? What I'm going to do is, I know, first of all, I can only, right, this is like a mathematical proof, right? I mean, you start off by saying, look, I can produce all these colors over here. How do I produce the colors on this arc? I take a pure spectral source of light, right? This is a pure spectral source of light. So I can produce any color on that pure spectral source, right? And then, now if I take 2 points on this arc and I mix them together, I can get any combination of color. I can get any color on the line connecting them, because I know that's what will happen with a projection. So as long as I take 2 values that on opposite sides, I can get the straight line connecting them, and I can get that color. So there's more than one way to produce the same color. It's not unique. All right? And now, how do I produce that color? Yeah.
I have a question, but I guess I'm not.
Yeah, that's fine.
Here, when we get these 2 pure spectra, add them together to generate new color. The problem is that these new colors have higher energy. So, if we consider the uniform line, then the new color is uniform line.
Well, okay, so there's a few issues there. I mean, one is that, as I said before, this chromaticity has many colors associated with it, right? So there's many colors that produce the same chromaticity, and the difference is the brightness of the color, the lightness. Okay. So when you add the pure sources together and you get something brighter, that's changing the lightness, okay, which is important. And an important component of color, but it's not an important component of chromaticity. Okay. Now, the other thing is this, and the other thing is sort of more of a comment, which is, and it gets back to this idea of metamers. Okay, that you have a source of white light. This is what's called equal energy white light, going from 400 nanometers to 800 nanometers. It's constant. Okay. So it's a constant, whatever value. Let's just, without loss of generality, let's say it's 1. Okay. So is that the only? You can have a different spectrum that produces the exact same sensation of exact same color, the same perception of color, all things being equal, in the sense of color matching. Okay. And that spectrum could look crazy. Okay. I mean, I'm just going to make something up. I mean, it would be interesting to generate some kind of simulation that color match. So with two pure spectral lines, or three pure spectral lines, you can match this. So this spectrum looks completely different than that, but they'll produce the same perception of color. And these are called metamers, okay? Because it's only a three-dimensional space, so you only need 3 degrees of freedom. Now, you can't always match the white light with any 3 colors, but certainly with these 3 colors you could, okay? Okay? Basically, because one of these would look red, green, and blue roughly, and some combination of them we'll see in a moment will produce a white, okay? So does that help clarify your question? Yeah.
So basically, every color inside that horseshoe is brighter than on the curve.
If you actually produced it by adding the light on the sides, that's correct. Then you could attenuate it with say a neutral gray attenuator, okay, and you could match it. But yeah, the key issue is that for a specific chromaticity, there's an infinite number of colors that correspond to that chromaticity, and for a particular color, there's an infinite number of spectra which will produce the same color. Okay. It's important to get this whole thing, your head around the whole thing all at once, okay? Now, here is the really interesting part. What happens is, let's say you have a display on a computer, say. So, a display on a computer maybe has a green, this is going to be a blue, and a red, okay? So this is going to be R, this is going to be G, and this is going to be B, okay? So this is the chromaticity of the blue on the monitor. This is the chromaticity of the red on the monitor, and this is the chromaticity on the green. Assuming the display is additive in the sense that the spectrum of light coming from the display is the sum of the individual components of light, which is reasonable to assume. Okay. Assuming there aren't kind of weird interactions in the electronics, like if the power supplies interacted, then when you put one gun on, it would draw down the power supply and might make the other gun less bright or something like that. But in any case, so assuming no nonlinear weird interactions, then if you take the green and the blue and you mix them together, you're going to get a color along these lines. Okay. And these individual green and blues were themselves made up by some combination of pure spectral components. And if you took the green and the red, you're going to get colors along that line. And if you took the blue and the red, you're going to get colors along that line. So if you take any positive combination of red, green, and blue, you're going to get, I shouldn't say colors, you're going to get chromaticities that fall inside of this triangle. So you can certainly produce any color that falls within this triangle. Furthermore, you can't produce any color that falls outside the triangle. Because if you fall outside the triangle, there's no way, when we took, one of the key points was that whenever we took a linear combination of two colors, it had to fall somewhere on the line connecting them. So you can't produce any colors outside of this triangle. So now over here, can you produce that color on the display? No. But does that color exist? Yes. How would you produce it?
Map it to a nearest color.
You would have to take two colors in the spectra that pass through it. A combination of those two pure spectral colors will produce that color. But the problem is it falls outside the range of colors that can be produced by the display. So, this thing here is known as the gamut of the display. Because it's the range of colors the display can produce. So not all displays or printers can produce all colors. In fact, any real display or printer can only produce a subset of all real colors in practice. And well, I mean, I don't know. I guess it'd be theoretically possible to build a display that what it would have to do is it would have to have a tunable laser that would be able to be used as the light source, for every pixel kind of a thing. It would be totally impractical, okay? But for any practical display, it will always have a gamut which is limited. It will never have a gamut which it can produce all possible colors, because the sources of primaries are limited. First of all, typically they'll be far away from the pure spectral sources. The more pure the spectral source, the wider the gamut generally. But even if you had perfectly pure spectral primaries, you still couldn't produce all colors, because this is curved, okay? And these lines are straight. So the triangle can only fill up most of this area. It can't fill it all up. Furthermore, here's the cool part where this is my own personal favorite aha moment, that like, okay, so the question people always ask is, well, what's an imaginary color? What do you mean that the color primaries for X, Y, Z are imaginary? Well, they're out here, okay? This is the color primary for X, because if you just have a value which is X and Y and Z are 0, then its chromaticity would be there. But this falls outside the range of all visible colors. It's mathematically, I mean, we can represent it mathematically. We could pretend that color exists. But it doesn't, because there's no physical stimulus which will cause a human to respond like that, okay? And this is the primary color for Y, and this is the primary color for Z. So you can see that it's sort of like this triangle here represents the gamut of a display that could have physical colors that correspond to the XYZ primaries, except for, it doesn't really exist. Okay? This is like some, imaginary science fiction display. Okay? These real displays always have to fall inside of the real visible colors. Now, you can have on your computer, you can have a display where you have a digital preprocessor so that it takes its inputs as XYZ, and then what it does is when it uses that command, and then it tries its best. Now, if you give it a value that falls outside the gamut it can really produce, then it has to do something. It could provide an error message. What it'll really do is it'll map it to the closest color that will provide, make people as happy as possible. It's like, you went to go buy a car and you said, well, how much? And whenever you go to buy a car, the salesman always asks you, what do you want to pay for this car? And my answer is $1. And they go, well, I can't. Okay, what's the best you can do? So $1 isn't plausible. So we'll have to fudge it and find something in gamut. Okay, that's as close as possible. And close as possible is hard to determine. Okay, so right. So good. So now what happens is and then white, by the way, is in the center. By the way, white is equal energy white is X equals Y equals Z, right? It could equal 1, but equals any value. So this is EE white point, okay? And so that implies that little x, little y equals 1/3, 1/3. So if little x, little y equals 1/3, 1/3, then this is going to be here, and that's going to be where white. That's equal energy white, which is not actually commonly used. Equal energy white is not commonly used, but it's a good reference point. Okay, so here's the mathematically generated chromaticity diagrams, and you may have actually done them in your lab. Hopefully you did, and they may have looked better than this. But here's equal energy white. There's D65 white. Now we begin to understand what's going on. For the CIE standard, the RGB color primaries were pure spectral components. That wasn't practical, but it's great for doing an experimental measurement because you get a very wide gamut. Okay? But for a practical display, you don't want to use those because you can't practically produce those colors, at least at modest cost. So real colors tend to be spectrally less pure. Now, these 709 color primaries are pretty much widely adopted by this industry for all kinds of applications, ranging from TVs to computer displays. They're pretty widely used, and they give a pretty broad gamut. Okay, but there are definitely colors that can fall out of gamut. The other thing that's interesting is that now what we can see that, well, gee, if you were doing this using the CIA color primers and you were doing this color matching experiment, that if you tried to color match a reference over here that was a pure color over here, right? What would happen? Could you match that color with these three spectral primaries? No. Because no linear combination of these things will produce that, right? So let's say I try to match that color right there, okay? So what I could do is I'd say, well, okay, I'll draw a straight line here. So that point of intersection, I could produce that color by taking a combination of red and green, red and blue, okay? But to get that color, to match that color, I need negative red. Because any positive red will pull me on this side. I can show if red is negative, it will actually send me over here. So what this means is that this is, when we did our color matching experiments, we needed negative red over here. That meant our color matching function was negative there. So now we have this beautiful interpretation of what it means for the color matching function to be negative. See, I told you that that eventually, if you hung on long enough, this would all kind of fit together. Let's look at the color matching function. I need to get my color matching. Okay, oh, here it is. Sure enough, see, the red is negative. See, and this was like, well, this isn't labeled, but that might be, say, I don't know, 500 nanometers or something, okay? That might, because you can, I think it's like every 10 nanometers, so that's 400, 410. You can see the little vertices because of MATLAB. 420, 430, 440. So this is like that's 450, so this is like, I wasn't that far off, 445 or something, right? So this is right around here, and it's negative. Okay, so now what you can see is actually, not only is it negative sometimes, it's one of the tristimulus, one of the color matching functions is negative almost always, okay? Because what happens is this is a curved surface, so this always extends out the straight line. This will be negative a lot, okay? Then over here, you'd expect it to be slightly negative also, because that curve, the black curve is going to be just a little bit outside of the straight line, but it's pretty close. You know, here you're pretty good. But here, you know, you're not. And that's exactly what we're seeing here. That you see the red goes way down, but these don't go so negative. But that's why you need negative color matching functions, because this horseshoe shape falls outside of the triangle. And at the actual vertices of the triangle, you're right on the curve. Because the vertices of the triangle represent pure spectral components, and by definition, they're right on that curve. Okay. Now, there's a few other points I want to make. So basically, what happens is this. I also, because I often do this on the test as a way of testing. Okay. So you get this curve like this. So this is the triangle. These are real colors, but they're not they can't be displayed by this device, okay? This physical device. These are not real colors, they're imaginary colors. Now over here, if this is your particular color coordinate system for the particular primaries you've chosen, then all this region here represents negative red. basically, any region where you fall outside of this thing will produce a negative value of the tristimulus, corresponding tristimulus. So that's what happens. You need to be able to support, if you want to have full gamut, you have to be able to support negative values of RGB. We'll talk about it some more next time. Thanks. Bye.